Hey, Flipped Chemistry, how you doing? Are you ready for another lecture? I am. Let's jump right into it. We are talking today about how to calculate pH and POH. And I'm going to give you a quick little introduction to the pH scale and what it means to be an acid or a base. So you've heard about the pH scale before. This is not a new concept to you, even though we haven't covered it directly in chemistry yet. We dealt with it a little bit in physical science and just being alive. You've heard of acids and bases. So here we go. The pH scale is a way of expressing the strength of an acid or a base. The closer a pH value is to, it says 1, the answer is actually 0, the stronger the acid. And the closer the pH value is to 14, the stronger the base. So we're looking at how concentrated is the solution in hydrogen ions, hydronium ions specifically. So 0, pH of 0 is incredibly concentrated, pH of 14 is not so concentrated, and you will see why the numbers aren't maybe the way you think it would. You think that a higher number means a more concentration. I'll explain the math in a minute, and it does make sense. A pH of 7, right in the middle, is neutral. Distilled water, which I happen to be drinking today, is purely neutral, and is, as a matter of fact, the definition of a neutral solution. Okay, so pH scale. Stomach acid, hydrochloric acid, is about as acidic as it gets at pH of 0. Drain cleaner, Drano, lye, very, 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 very basic, and pH of 14. Right in the middle, distilled water. Milk and blood are oh so slightly off of that, just a little bit off of that. And then some foods get pretty acidic, and some cleaners get pretty basic. So there's things that you're used to seeing and using in your real life. The POH scale, a little bit confusing, it's exactly the opposite as the pH scale. We're looking instead of the concentration of hydrogen, we're looking at the concentration of hydroxide. OH is a group that you will see in lots of bases, and so that hydroxide ion, we're looking at the concentration of that. Very low numbers in the POH scale means lots of hydroxide, very concentrated, strong base. High numbers on the POH scale, not so concentrated, and more of an acid. So 7 is still neutral. The pH or the POH scale is based on what a substance does to water. So that's kind of confusing because at first you might think it's how many hydrogen ions there are. Well, yes, but not really. We look at what the hydrogen ions do to water, and then we measure how prevalent that modified water molecule is. I'll show you a picture in just a moment. pH measures the concentration of hydrogen ions produced, and the POH measures the concentration of the hydroxide ions produced. Okay, so just a real quick picture. This is hydrochloric acid plus water, and when we add granular hydrochloric acid to liquid water, we get this hydronium ion. So the hydrogen here jumps onto the oxygen, and we wind up with H3O, which is a positive polyatomic ion called hydronium, and then ionized chlorine in the water. Just another picture of that. Hydronium looks like this. And POH, similarly, NaOH, when it gets into water, it dissociates, and so the sodiums become a positive ion, and the hydroxide ions become a negative ion. We look at the concentration of those for the POH scale. Okay. Now, pH and POH are mirror images of each other, so if you have a pH, you can calculate POH. If you have POH, you can calculate pH, and you do that by just taking the difference to 14. So if something has a pH of 2, it has a POH of 10. If something has a POH of 7, it has a pH of 7. You just see, what do I have to add to this to make 14? Okay. Now, the pH, this is the math part. pH, or POH, is the negative log of the ion's molarity. I'll say that again. It's the negative log of the ion's molarity. So molarity, moles per liter, right? And we express that moles per liter in scientific notation using 1 as the coefficient. So it has to be, concentration is 1 times 10 to the something. Now, it's always going to be a small number, times 10 to the negative something or other. And so it's the negative log. We take the exponent there, and we take the absolute value of it, essentially. We get rid of the negative sign. So if the concentration is 1 times 10 to the negative 6th molarity, then the negative 6 is what I'm after, and I whack that negative off of it, so the pH is 6, right? The negative log of 1 times 10 to the negative 6 is negative 6. Negative of a negative is 6. And we need to have this be 1 times 10 to the something. And if you are given a concentration of like 3.2 times 10 to the negative 4, you can't just do negative 4 and say that 4 is the pH. You've got to render that to a decimal, 1 times 10 to the some kind of decimal, and that's the number that turns into the pH. You're going to want to ask your calculator to do that for you. So sometimes it's a little bit crazy, but you've got to do a little bit of math. But once you have 1 times 10 to the something, that something is the pH. Okay, pretty simple. Here's the operation could go backwards as well. If you're given a pH, just make that the exponent of 1 times 10 to the something, add a negative sign, and you've got the concentration, the molarity. So pH of 9, what's the molarity? It's 1 times 10 to the negative 9. Okay, pretty simple. Some substances can be both an acid or a base. We call those amphoteric. They can be both functionalities. They can swing both ways. An amphoteric substance tends not to be equally awesome at being an acid or a base. Some substances are a better base than they are an acid. Some are a better acid than they are a base. But amphoteric substances can behave both ways. They can both donate electrons and receive electrons, or they can both donate protons and receive protons. So water is a good example of an amphoteric substance. It can behave like an acid or like a base, but it's actually a pretty weak acid and a pretty weak base in both cases. Some other ones can behave better as an acid than as a base, but they can still function the other way if they need to, depending on the chemistry. And then the last concept here on this slide is a polyprotic acid, and the word is just what it means. Poly, more than one, protic, proton, more than one proton in an acid. So the formulas of acids are always written with H as the leading atom. So HCl is a monoprotic acid. It only has one proton, one hydrogen. Here, H2S has 2 hydrogens, so it's a diprotic acid. It's a polyprotic acid. H3PO4, 3 protons. H3, a triprotic acid. So pretty simple idea. If you see an acid written as an H and then something, and there's more than one H, it's a polyprotic acid. These tend to be pretty potent acids because when they ionize in solution, they can give 2 protons to water and make 2 hydronium ions instead of just 1 that a monoprotic acid would do. So they, in smaller quantities, tend to lower the pH faster. Okay? pH is measured a couple of different ways. We can measure pH with color shifting indicators like litmus paper or cabbage juice or even red wine, all kinds of natural substances that change color in the presence of acids or bases, or with a pH probe, which looks like this. Now, a pH probe is pretty darn expensive. We don't have any here at the school, but there's one. Now you've seen it. And what it does is it takes a reference pH from distilled water, remembers what that's like, and then you stick it in not distilled water, you stick it in something else, and it tells you the pH as a comparison of the hydrogen content. They're pretty tricky to use. You have to calibrate them all the time, and they're very expensive, which is why we don't have them. But if you take chemistry in college, you will probably play with at least one of these at least once. Okay? That is it, ladies and gentlemen. pH and POH, acids and bases. If you have any questions, put them in the comments field below, or see me tomorrow in class, and we'll slog through it together. God bless you. Jesus loves you, and so do I.